Okay, so now it's 9:21. So go ahead, Terry.
All right. Do we all see my slides? Are we good?
And I can hear you too.
All right, good. Okay, so I'm going to be building off of what Katie just taught everyone about some amino acid biosynthesis, but some different amino acids. First, we're going to start by looking at the sulfur containing amino acids, and then we'll look at the biosynthesis of proline, ornithine, arginine, and their mechanisms, and same with valine, leucine, isoleucine, serine, and glycine. Okay, so first we're going to start with sulfur-containing amino acids, like I said, and to get from inorganic sulfate, which is the major precursor, most plants and bacteria use this PAPS intermediate to make sulfide. The sulfide is the major group that actually does like organic reactions and binds to important organic structures. So it does this by using some energy, but this ATP is kind of cool because instead of like using the phosphate groups for energy, it actually attaches the adenosine and the other phosphate group directly to the sulfate. And then here, the second part, is my thing not moving?
No.
Oh.
It only just did for me.
Now
Whoa.
it seems with sulfur.
That's a pretty picture.
Thank you. Okay, here we go. Sorry. Okay, here I was talking about so this adenosine triphosphate actually binds to the sulfate, and then the ATP here uses, like more traditionally, uses the phosphate group and phosphorylates this, and then it makes this PAPS, this 3-phosphoadenosine 5-phosphosulfate. Then that gets reduced with the presence of an enzyme called thioredoxin, and that makes this sulfite ion plus this, which is not needed, and the sulfite ion gets reduced more and gets all those oxygens popped off by an enzyme called sulfate reductase, and then we end up with the sulfide. So this sulfide is then used in bacteria, like this top path, to make cytosine, and it does this by an enzyme called peroxidyl phosphate dependent enzyme, and it just like gets these close enough to where they're able to react. And then this pathways in plants, and they have to have this intermediate step that makes O-acetylserine, and they do this with a different enzyme. And the big result is this cytosine. So, like Katie talked about, methionine is essential for mammals. We're not able to make it ourselves, but bacteria and plants can. And because we can't make this methionine, which has a sulfur group, we have to consume it to be able to make all of these things in the pathway. So instead of starting at methionine or at serine and going down to methionine, we're going to start at methionine and go back to cytosine. So,
Sorry, one comment. It's a cysteine, not cytosine.
Cysteine? Sorry. Yes.
Cysteine, yep.
I'm sure I'll butcher some more names by the time we're done. So this methionine initially donates its methyl group to this adomet, which is short for S-adenzosulmethionine. And then it becomes this homocytosine. This homocytosine is then condensed with a serine group by this cytosine beta synthase to make this cytothione. So this is a kind of cool reaction because we start with a 4-carbon, and this 4-carbon molecule has the sulfur group, and then we have this 3-carbon serine, and then we have this intermediate here that actually has 7 carbons plus the sulfur group, and then this cytosine gets broken in two to make this cytosine that now has the 3-carbon backbone of the serine, but it also has the sulfur group now. And then we have this leftover alpha ketoglutarate, which is the 4-carbon backbone, but it doesn't have the sulfur. So it gets changed from this. The sulfur goes from like this homocytosine to this serine. And this cytosine can be used for like glutathione. It can also be used to make some free amino acid called taurine, Taurine, and it's used in Red Bull and like some weird energy drinks in like a large quantity. I think it said 1,000 milligrams per can. So drink that, I guess, if you want to.
What compound was it?
Taurine, Taurine. It's a free amino acid.
Yeah, it's taurine, Taurine.
I'm not going to go over the degradation of sulfur containing amino acids too much. It's very similar to what we just talked about, going from this methionine down to cytosine and alpha ketoglutarate. And then just after that, we reduce it. And then there's a few more little steps here that doesn't really talk about. It just says happens. And we end up with succinyl-CoA. And that's how it's broken down. And the sulfur gets caught up in the cytosine down here. And that's where that sulfur group goes. And then we're just ended up with oxygens and carbons for whatever it needs to be done with. So now that we've learned about sulfur-containing amino groups, we're going to switch over to proline, ornithine, and arginine. So proline, ornithine, and arginine all start with glutamate, which is usually got from the glycolysis. So we start here by reducing. Actually, we phosphorylate first. We phosphorylate this glutamate, and then we end up reducing it to get this glutamate gamma semialdehyde. This glutamate gamma semialdehyde has a cyclic tautomer that it's in equilibrium with, and this tautomer gets reduced with NADH right here to actually form proline, and it gets reduced with a enzyme called delta proline 5 carboxylate reductase. Then we end up with proline. Now if we go down the other path, we have another glutamate that has its amine group transferred to the glutamate gamma semialdehyde to get another alpha ketoglutarate, which we will use for other amino acid synthesis. And then we get this ornithine, which is important. It's a little vague, but this ornithine goes through the urea cycle, through all these little pathways to finally get arginine. Now, all of this is also can go in reverse. If you look, there's lots of equilibrium arrows and stuff, and it's mostly just regulated by different enzymes. So to go from like glutamate to here, we used delta proline 5 carboxylate, but if we go back, we use a different enzyme. So we now have 2 of these alpha ketoglutarates from the 2 previous amino acid steps, and we can use those to make isoleucine, valine, and leucine. The book's pretty vague about how they're actually made. It just says a lot of different complicated steps. So we're not going to talk about it too much, but they are all self-regulating. So this isoleucine will actually inhibit this serine 3-adenine dehydrogenase if there's a lot of it, and it won't like go any farther in the pathway. Same with this valine. If there's a lot of valine, this won't happen. A lot of leucine, this won't happen. And they're mostly made as parts of proteins if they're used, and then they're also just used for like destroying other like valines or leucines they don't need. So they use the amino acids to destroy the amino acids. Okay, synthesis of serine and glycine. So glycine and serine are very similar. We start by using the 3-phosphoglycerate from glycolysis, and we oxidize it with NAD+. So, what?
2 more minutes.
Okay, the ketone form, 3-phosphodroxypyruvate, then gets transamination, so it adds an amine group here, and then this gets dephosphorylated to end up with serine. And the serine group goes through a serine hydroxyl transferase enzyme and is changed into glycine through the hydroxyl methyltransferase reaction. Okay, these are my sources. Do you guys have any questions?
Yeah, I was actually curious. What is the main function of ornithine? I've just never heard of it before.
I haven't either. The way I understood it, it only has to do with the urea cycle and making arginine. The exact like function of it in that cycle wasn't very well taught from the book, so I'm not completely sure.
Okay, thank you.
Back to that slide of
Oh, yep.
amino acid synthesis.
Which one was it? That's too far.
I think you went too far.
This one, yeah.
Yeah. So it's a part of urea cycle. It's there just to do urea cycle. I think that's a way to understand ornithine.
Okay.
So ornithine stick with carbamoyl phosphate and make arginine. Now, okay, then let me ask a question to Terry. It may be a little beyond your scope because urea cycle was explained by someone else before, but why do you think this urea cycle exists?
The urea cycle exists to get rid of nitrogens, right? To excrete nitrogens we don't want.
Yep, right. So it has two roles. One role is obviously for arginine synthesis. So when someone needs arginine, this is a way. Make arginine. But in other case, it's just cycles and dispose nitrogen as a urea.
Right here. Okay.
Yeah, rather than as ammonia. So when it was a urea cycle, I think you saw another cycle connected to this cycle. The point is ammonia is toxic, so let's pick it up and convert it to urea by sticking together with something else.
Okay.
And something else comes from carbamoyl phosphate. So, yep, overall ornithine is just there to connect those cycles. So like, let's say like acetyl-CoA. That one itself, we don't really use it, but that one is the one connecting the cycles. Okay, is there any other question?
I have a quick question. So you mentioned that we need methionine from dietary because we don't necessarily produce it in our body. What dietary products are we talking about when it comes like loaded with methionine?
So like I said before, plants and bacteria are big on making methionine. They're like the major producers. So just any animals that eat plants or the plants themselves is how you get dietary methionine. It's used in a ton of proteins, so there's a lot of it. Usually most healthy people will meet the dietary requirement and be able to make all this cytosine stuff, and this methionine can actually get excreted, like I said here, if we have too much of it.
Okay, thank you.
Yeah, I have a question.
Mm-hmm.
So, why can't mammals fix serine to cysteine and plants can?
That's a good question. I wish I could answer it. I'm not sure. I think it has something to do with we don't need to because we eat methionine. So I don't think we have to do it, so we don't. But I'm not positive.
Okay, thank you.
Yeah, I believe along the evolutionary pathways, animals dropped certain enzymes because it's we can just eat it, and if we don't eat, we die anyway. So that's my guess. But if anyone eat like a protein supplement, for example, if you only eat soys, for example, then that lacks some of the essential amino acids, or it's a low in essential amino acids. So every species kind of varies in terms of the content of the amino acids. So yeah, anyway, that's kind of interesting information. Why? I would answer first, we lack enzyme, we lack pathways. And that should come from some evolutionary pressure, I believe. Okay, is there any other question?
I had a question.
Go ahead.
On like the second or third slide, you had the intermediate, I think it was 3-phospho AMP before this. Yeah, right there.
Yes.
And you said it's not needed. Do you know what happens to it? Is it just degraded or?
I do not. It doesn't mention it at all. It just says it's the intermediate. Yeah. No, it doesn't say anything about it in the book. I'm not sure where it goes. I haven't seen anything that we've covered yet that I don't think that uses 3-phospho AMP, but I could definitely be wrong. Yeah, I'm not sure.
Okay, thank you.
Okay, if no other question, I think we would say it's fine. By the way, so last question, it may not be used, but the phosphate group is easy to hydrolyze. So my guess is it will get hydrolyzed and go back to AMP. But that's my guess. It may be used in something else. It's possible. Okay, is there any other question? If not, let's move on to the, thank you, Terry. And let's move on to the last speaker of today, Sarah. Yay.
All right. I would like to apologize in advance. My cat has the Zoom